Hey guys, today we're going to take a look at continuity. So, first of all, we're going to go through these 6 examples here, and we're just going to discuss whether or not the function is continuous, and if it's not continuous, why it's not continuous. So this is one of these concepts that actually seems kind of self-explanatory, and that's a good thing. So this first one, this is a continuous function. You can see there's nothing fancy about this. It's just a smooth curve, and there's nothing that disrupts it or anything. So this is continuous. Continuous. Whoops. All right. That's not an apostrophe. That's just messy writing. So we took a look at this next one. You can see this is some sort of cubic or something, but it's got a hole at x equals 2. So a hole is what we call a point discontinuity. Okay, so there's a hole. Okay, so there is a point discontinuity. Point discontinuity. And that would be at x equals 2. Okay. So, another example of discontinuity. We've got sort of this step here. So the line's coming along, and then at x equals 3, it jumps up and forms another different line. So this is called a jump discontinuity. So let me just... So, we have a jump discontinuity. And that's at x equals 3. Okay? And so you'll notice that we're identifying where these discontinuities take place, and that's generally how this is done, because the function itself is continuous everywhere else. It's just at x equals 3 that it is not continuous. I did spell continuous wrong right here. Hold on, let's just correct this. Continuous. Did I spell? Oh my goodness. Whatever. Anyway, so if we jump down here, you'll notice we got another hole. So this is discontinuity. So discontinuous at x equals 2. And I'm just going to do this because it is a point discontinuity. Okay. So our next one here, we've got an absolute value function here. Now this is one that sometimes people will confuse with a discontinuous function, but because it's got this point here. But a point, like, just because it comes to a point like that doesn't actually make it discontinuous. There's nothing to prevent that from it. The graph doesn't have any sort of break or anything like that. So this actually is continuous. Okay. There we go. All right. And then finally, we've got one that has an asymptote. Okay, now an asymptote, a vertical asymptote, does indeed make it discontinuous. Discontinuous. And that is called an infinite discontinuity. Infinite. Okay, infinite discontinuity, and that would be at x equals 3. Whoops. Oh, for crying out loud. There we go. All right. Okay. So, in general, how do we know if something is continuous? What are the rules? Well, for a function to be continuous at a point, first of all, the limit as x approaches a from the left of the function must equal the limit as x approaches a from the right. Okay, so you'll notice that is just another way of saying that the limit must exist at that point. So there must exist a limit. But what's more than that, also the limit as x approaches a of f of x must equal f of a. Okay, so this is the criteria. So all of this will lead to continuous at x equals a. Okay, so that's what we need. We need the limit to exist, or in other words, the limit from the left side has to equal the limit from the right side, and that limit must equal the f of a, where x is the point where, or sorry, a is the value that we're interested in. Okay. All right, so let's take a look at some examples. Okay. So let's see. There we go. All right. So the first one we're going to look at, we've got a cubic function here. Okay. So this is fairly easy. So first of all, there's two things that we're going to look at here. We're going to say, well, the limit, okay, as x approaches 3, sorry, and then we were determining if it's continuous at 3. I kind of glossed over that, but the limit as x approaches 3 of f of x is going to equal, and there's nothing to prevent us from just doing direct substitution here, so we can do 3 cubed minus 3 squared plus x equals, and that equals 21. Okay, so the limit equals 21, and what's more, f of 3 also equals 21. So this is continuous. And a little trick is that anytime you have a polynomial, any polynomial will be continuous throughout the entire function. So any polynomial, anytime you've got a cubic, quartic, whatever, quadratic, doesn't matter. If it's a polynomial, it is continuous throughout. Okay? Now, if we take a look over here, we've got something a little trickier. Now, this could just end up being a whole, having this x minus 3, and actually that is what it's going to work out to be, but that doesn't really matter. We don't even have to do that much, because for this particular one, I can just say f of 3 does not exist. Okay? F of 3 does not exist because that we'd be dividing by 0. Now, it might be an asymptote, it might be a whole. It is actually a whole, but that's enough for us to know that that's discontinuous. Okay. Sorry, at x equals 3. Okay. So we'll look at this next one. Okay, and you'll notice this is exactly the same, except that I'm saying x does not equal 3, and instead f of 3 equals 4. Okay, so it's taking that same function, it's just adding a point in there. So hopefully that will take care of the problem with the whole. And if we look, we can say the limit as x approaches 3 of x squared minus 2x minus 3 over x minus 3 is going to equal the limit as x approaches 3 of x minus 3 x plus 1. So I've just factored the top there. I get x minus 3, that and that cancel out. And we're left with the limit as x approaches 3 of x plus 1, which there's no reason to prevent us from direct substitution at this point, so that would just equal 3 plus 1, which is 4. Okay, so the limit equals 4, and we've already been given that f of 3 equals 4. So there was just a hole there at x equals 3, and because it gives us that f of 3 equals 4, that takes care of that problem. So therefore, this one is continuous. Okay. All right. So let's jump over to this one over here. Okay. We've got 1 over x minus 3 squared. So this one's fairly simple. F of 3, well, if you sub to 3, you'd be dividing by 0, so that does not exist. So this one is discontinuous. Okay, and actually another little trick, a little rule here, is if you've got a polynomial over a polynomial, it is continuous everywhere except where the bottom would equal 0. Okay? Anyway, so let's jump down to our last one. I didn't really give us enough room here, but that's okay. So this one, because we got a piecewise function, what we're going to be interested in is we're going to take a look at the limit from both sides. Okay? So the first thing I'm going to do is I'm going to say the limit as x approaches 3. And we'll go from the left. So from the left, that would be this one here, this guy right here. Okay. So 7 minus x squared. And there's nothing to prevent us from using direct substitution, so we get 7 minus 3 squared, which is just going to give us negative 2. Okay? So the left-sided limit is negative 2. So for the right side, the limit as x approaches 3 from the right, and the function is just 2. And so the answer would just equal 2. And because negative 2 and positive 2 do not equal each other, we can say, therefore, the limit doesn't exist, so therefore this is discontinuous. At x equals 3. Okay. And that's that. So let's take a look at another example here. This one we're going to graph it first so that it's clear what we're doing. So when x is less than or equal to negative 1, it's going to be x squared minus 3. So you're going to have to think back to your grade 10 math, and you'll know that this is going to look like we're going to have a point there. The vertex would be on the x-axis or on the y-axis, but it's not going to be. We'll have a point there, and we'll have a point there. So it's going to go like that. And then when x is greater than negative 1, it's going to be x minus 1, which will give us a point there, point there, point there. So we're just going to have, it's very difficult to draw straight on this thing, but there it is. Okay? And so if we look at this, you can see the left-sided limit as we come down, here, as we come down this way, you can see it's approaching negative 2. So the left-sided, or the left-sided limit is negative 2. And if we come down the other way, like that, we're also heading to the negative 2. So it is also negative 2. So that just tells us that the limit of f of x as x approaches negative 1 is just equal to negative 2. Okay? the function at -1. So when it equals -1, so we would be using this one right here. Okay, so it's the x squared minus 3. But we can just sub in -1 squared minus 3, which would, of course, give us -2. And we could have just looked at the graph and seen that. But that tells us that, so the answer, whoops, oh, I don't even know what I did. There we go. So the answer to B, I did not mean to switch to red there. Whatever. The answer to part B is equal to the answer to part C. So therefore, this is continuous. All right, and that's all there is to it. Okay. So this last question is a little bit more challenging, and this is the one that I want you to give it a whirl. And at the beginning of class, we're all going to take up this question. Okay? So that's it. Thanks very much.